Thank you for staying up until the very last session. And I'm here to talk to you about RunX. Hopefully you'll enjoy the presentation. RunX is a new OCI-compatible containers runtime to start containers as Zen VM. So let me dig immediately into what that means. So if you look at these slides, so normally containerd handle the container in terms of an image, in terms of a package that is compliant to the OCI image specification, and then calls into RunC to run actually the container. And what RunC does is sets up a set of Linux namespaces to run the application inside the chroot environment, plus a lot more of namespaces. But the container does not really need to be executed using a chroot or anything else. So RunX works at the same level as RunC. So you can think of it as a RunC replacement that instead runs your container as a Xen VM. Now, when I say Xen VM, I don't mean a very large or a traditional VM with Debian inside, and then you have Docker inside the VM itself to run the container. No, this is a micro VM, as small as possible. It's tiny and is just enough just to run your container application inside the virtual machine. Going back to RunX, and then I'm gonna dig into the implementation choices later. But let me start by saying that it's aimed at embedded. So it's aimed at being very simple, small, simple to build and simple to run. And they have also just a very minimal overhead, so being able to run on small systems. Support also real time and all the things that are important in embedded. Accelerators is definitely really key. So you can assign hardware accelerators to containers for containers application to use them. Secure by default in the sense that using a VM, you don't necessarily need to go and configure SE-Linux to have a minimum level of security. So the project, as an open source project, is started under LF Edge, the Linux Foundation Edge umbrella, in collaboration with DDIDA. It's set up with a permissive license, Apache v2, and has been open to contribution from the start. You can just check out the mailing list and send patches. So as we've seen, the way it works is a container gets deployed through Kubernetes to containerd on the host, and then at the time of invoking RunC, you instead configure containerd to run RunX. RunX gets executed, and RunX will start your container as a VM, providing a small kernel and a small run disk, just enough to run your container. What are the top implementation choices? There are other projects such as Kata containers and more now that run containers as VMs. What makes RunX unique? Well, first of all, it has very, very minimal build dependencies. It only needs GCC, make, and go, and even the Go compiler is going to go away as a dependency soon. It's also easy to run in terms of runtime dependencies are very few. So in addition of Zen, of course, it only needs Bash, JQ, socket, and daemonize, and that's it. So in terms of simplicity, I think the key point is there are actually no ingest agents. So that means that once you start the VM, yes, there is a small kernel, Linux-based kernel, to be able to initialize the system for you, and a small initRD based on BusyBox just to initialize the minimal set of things that you need just before executing your container application. But aside from that, there is nothing inside the VM. Sometimes you find in other projects like a daemon, an agent that is provided by, let's say, RunX or the equivalent components to run inside the VM and stay there for the duration to send messages and communicate with the host. There is nothing like that here. So this is just a minimal kernel plus BusyBox-based RAM disk that doesn't really need any daemons to run. And in fact, you can think of the container environment inside the VM to be the pristine container environment in the sense that there is nothing but the container and the kernel that are running. So it's Also small, as I said, in the sense of the VM itself is small. So Xen has always had a lot of choices in the matter of how you create the virtual machine, choices that sometimes add complexity. But in case like this, they're very useful because you can set up a VM which is really, really small, very minimal, that doesn't do any device emulation. There is no in-guest firmware, no UEFI, no nothing, no BIOS inside the VM. So it's really small, no grab, nothing. So just straight kernel boot. Finally, it's OCI runtime spec compliant. So the OCI runtime spec really has come a long way. It's very complete now. It's a good spec. And by working against a spec, now RunX is actually compatible, at least in theory, with any container engine. So we have been developing it together with Containerd. We're not really done a lot of testing with other container engines, but at an architectural level, you should be able to use it with any other container engine. How do you build RunX? So if you want to build it on your Linux distro, you just need the Linaro cross compilation toolchain. You need the Golang compiler, again, soon to be removed, but the distro Golang package is sufficient, and it's just going to cross compile. So just set arch to AR64, you set up the cross-compile environmental variable, the go-root environmental variable that, again, is going to soon disappear, and the compilation will take care of itself. At runtime, you just need to install the RunX main script and the directory user share RunX to the target, and configure Containerd to use RunX instead of runc. With the 2 lines you see here on the screen to config.toml, and you're gonna get RunX running by default. Of course, the best way to run RunX is really with a tailored environment. This is where I'm gonna leave it to Bruce to continue.
It's funny, I wasn't ready for that transition. Sorry. Must be late. Yeah, I've been helping out Stefano, and we've been working through this. And I was taking care of making sure that not only could we do that simplified, distro-based build that he was talking about, that that we could do a full Yocto build. So so you could build an entire platform, containers, everything sort of all in one go. Everything I'm going to talk about and present quickly is now either pending, patches are out, or it's upstream into the master branches of the various repositories. So RunX has been in meta virtualization for a while. So is Xen and all of the supporting components. So that's where most of this work happened, as well as some of the reference work we did with Meta-Xilinx. So the question is, and it doesn't require Meta-Xilinx. This is when we do our demo, of course, we were using I was using a Xilinx QEMU to sort of have a more complex environment to test it in. So, but the question would be, why would we want to use Yocto OE to build and deploy it? You automatically can leverage some of the core values of open embedded. So you'll get your license reports and your build history and your packaging and your customization and all the things that you might use open embedded for in general. And you can transition from sort of development and debug right to a production build just based on the recipes and the other build components you've pulled together. And that we can leverage this part where we have active sort of community and integration with BSB layers. And the example that I did was Meta-Xilinx, so we could test it on the platforms. And of course, we can leverage a fairly new bit of Yocto with these multi-config builds. So you can build the hosts, the guests, the containers, and firmware all in a single platform using multi-config capabilities of Yocto. I have a very quick, this is a little bit of when we were working through the demo, we captured some of the parts, and I put this out here, and there'll be readmes in meta virtualization. But this is quickly just we cloned the dependent layers, which is meta open embedded meta virtualization. In this example, Meta-Xilinx, initialize the ZC102 board, and then we add specific layers that are within those bigger layers that I cloned. And if we jump to the next, yeah, and there's just a tweak. This is sort of a local config, and some of this I will be merging into more of a distro configuration. So even maybe this part will go away, but this is just some, in case anybody wanted to try to reproduce this build on Yocto master. This is some stuff that we put into the local.conf right now to do a little bit of configuration, which will build the main board, the QEMU elements, as well as RunX and all the virtualization, and build a PMU firmware for a part of the boot. So it's using the multi-config. It's not building a container into the multi-config, but that's the next step that I'll add to the Yocto integration. All right, next. And then, you know, here it is. This is just a matter of showing this. The two, skip all this other stuff, is just preamble of, you know, if you weren't using multi-config, Xilinx has some pre-built components for our boards that you can use. But the important thing is you just really bit-bake Zen image minimal, and that will iterate through and build everything that you need for a working platform. And of course, here it is. Once that finishes, you can just test your basic boot with the core image minimal example I gave, which is just a simple small image. It'll boot to a prompt. Make sure that you have sanity of the QEMU platform or your hardware in this case, because actually that image will work for both. And then finally, to run all of the demos and all the testing we did, it's just run Zen image minimal, and that takes care of booting the whole system and dropping you into the prompt to start interacting with RunX or Containerd. Actually, you don't really interact directly with RunX to do this.
Okay, thank you, Bruce. Let me express some more advanced use cases that we'll demo, in fact, today. So, you know, it is interesting to be able to run a traditional container, and like Alpine Linux or any other container, something built with Yocto, anything, you're gonna get it deployed, and then RunX transparently is gonna run it as a VM, providing the kernel and the RAM disk. That's a basic use case, but you should realize that the RAM disk and the kernel inside the VM are really just optional, and they're really for compatibility. So the security boundary is the VM, is the virtual machine, is not the kernel and the RAM disk inside the VM. So of course you could take it one step further, and the container could also come with the kernel. So if the container came with its own kernel and told RunX about it, RunX would be more than happy to use the provided kernel or provided RAM disk inside the VM, because again, this has nothing to do with security. You just need to run a kernel inside the VM. You might as well run the one provided by the container. So the RAM disk is less interesting, but the kernel is interesting. So for instance, you could have a Linux RT version if you care about real time. You could have your own specific version of Linux you care about or you tested with. Or you could have the version of Linux with the right driver that you need. Because as you are going to see later, we are going to do direct hardware assignment to these container VMs. Therefore, your container environment will be able to use its own driver if so wishes to do. So this is useful for Linux, but you can take it even one step further more. So if you could package a non-Linux OS that way. For instance, an RTOS. You could package FreeRTOS or Zephyr as a container, deploy it through your Kubernetes cluster to Containerd. Containerd calls into RunX, and RunX runs the VM and then figures out there is a kernel inside. Doesn't matter what kernel. So far, I assume Linux, but it could be something else, and run the special kernel inside. And that way, you have a way to dynamically deploy RTOSes on your target. And so, as I mentioned, specific version of Linux is interesting, specific kernel configurations. Even more interesting, non-Linux OSes, including baremetal application, RTOSes, proprietary OSes, BXWorks, and so on. How does it work? You just need a way for the container to be able to flag that it contains a kernel. You just need to be able to say, here is my kernel binary. And we want to standardize new flags in the OCI image specification to do that, Today for the demo, what we've been using, and this is what is upstream in RunX, so it's not like for the demo, you can check out master and do it yourself, is using two special environmental variables, one called RunX kernel and one called RunX RAM disk. If set, RunX will look for them, and if set, will use the kernel and RAM disk specified there. Another thing that I'm going to show today, and I think it's very interesting, is direct hardware assignment, device assignment. So when you run your container, especially if it's an RTOS, you definitely want to assign directly hardware resources or accelerators, devices. And to do that, you can pass extra argument to RunX. So the administrator is a very data center word, but the person talking to containerd, or the set of software talking to containerd, can pass special flag to RunX to say, yes, I can see I have an RTOS container. I want to run this RTOS container with the TTC timer assigned to be extra precise in time accounting, or I want to directly assign this AI engine or FPGA block. And it is done through another special flag called accelerators that allow the user to add or edit any information for the creation of the virtual machine. So it can be used to increase or decrease the amount of memory, increase or decrease the amount of virtual CPUs, to set up real-time configurations, and also for device assignment. And there is an important distinction that this flag is only for the user or administrator. It's not really for the container. But, and this is not done yet, so it's not something you're going to find, not even in RunX master. But eventually, what we're going to be able to do is we want a container to be able to request an accelerating resource or an FPGA block. And in the case of FPGA blocks, the accelerator could even come with a bitstream itself. So you can imagine the accelerator containing maybe a Linux kernel or another kernel, user space binaries, and the bitstream, and say, I want this bitstream to be programmed into the programmable logic and the resulting block to be assigned to me. And then containerd will deploy it, use something like FPGA manager to program the FPGA with the bitstream, then call RunX with the right argument so that the container gets started as a VM with direct hardware access to the FPGA block. Yeah, and again, accelerators could be anything from FPGA blocks to AI kernels or just more traditional hardware resources. All right, I would like to spend the rest of the time on the demo. I'm gonna demo a couple of things. One of the things I'm gonna demo, I wanted to show you straight away, is the ability to start a baremetal application as a VM that has direct access to the TTC timer on the board. So here I have containerd already running. Containerd is already running. I have imported a few images, including Alpine Linux. This VM1 is a baremetal application, and VxWorks. So let's start actually from that. This is just a shortcut for me to have to type less. And there's a containerd CTR command to start VxWorks. And here we are. VxWorks started, and we have console connection to it. There was a VxWorks kernel packaged as a container, imported and run using containerd CTR. Containerd CTR calls RunX. RunX figures out this container contains a kernel. There is a RunX kernel set up appropriately, and you get a VM with VxWorks 7. And you can do things like check out the devices and so on. So you can see that there is a VM running if you call Excel, but there is also a container running if you use the containerd CTR command line. And the next thing I want to do, that's actually what I showed you on the slides, is I want to start a bare metal container passing accel_conf. So in this case, we are passing an extra flag, as you can see here. And the extra flag is to do device assignment. So the container itself comes already with a kernel and is already advertised in that kernel. But the device assignment is something we configure and we request through a config file like this that specifies that we want to, well, is giving the 64 megabyte of RAM to the container because it's really more than enough for a bare metal application, and directly assign interrupts and MMIO regions. If I run it, I'm going to switch to another serial because actually this is starting here. Previous is my previous test that I ran just before this presentation to make sure it's working. So as you can see, it's doing a latency measurement run, and that's directly assigned another serial. This is the second UART I'm connected with, and it's using the TTC timer, which is a second physical timer that has been directly dedicated to this container slash VM. And again, as you can see, now there are 2 containers running, and there are also 2 VMs running. Okay, so I think this is the end of the demo, and I will be more than happy to take any questions you might have on RunX. Okay, so if there are no questions, of course, we'll be reachable by email. Make sure to check out the mailing list that is present on the slides, and the RunX repository that is under just GitHub LFEdge RunX. So check it out, have a look, and make sure to try it, not just with your regular containers that is, it's expected, but also with more interesting containers, trying to repackage your FreeRTOS and FR binaries as containers and see how it works.